Welcome. We're going to take a look at some things here, in particular about our motor starters, our magnetic motor starters, um, the most specific. So, magnetic motor starters, if I could spell. And we're going to take a look at those in relation to the load. And now the reason why I'm spending some specific time here on that is because our motors are an amendatory section to the Canadian Electrical Code. The CEC looks at these under section 28. Okay, when we take a look at protection and control in a general sense, okay, this is an mandatory section in 28. For protection and control, general rules is section 14. Section 14. It doesn't pertain to our motors in this case because our motors have something called, well, they're an inductor. And when we power on an inductor, we see a massive surge, and then it's going to let up to its running current. We're going to call that our running current or operating current. Right here, that's what we would call our startup current. Now that could be up to 600% of what the running circuit will be. So as a result, section 14 is no longer valid for this. We're going to have to defer to section 28, which deals with our motors specifically. And when we do that, it's going to tell us that we're going to be looking at overcurrent devices, and we're also going to be looking at overload devices. Now, in our normal loading, when we have a load, I'm just going to draw this real quickly over here. We're going to take a look at an overall circuit breaker, and it's going to be protecting, I don't know, say a light. Okay, we're just protecting. Now, the process that we would do is we're going to take our load, and we're going to have to find out what the wire size is, the AUG size, and then we're going to figure out what the breaker size is using table 13. So all way we're making sure that this breaker is protecting everything down line of it. Okay, it's protecting the load, it's also protecting the conductors. This is not the case because of the inrush current. The inrush current, these overcurrent devices are going to be sized according to some pretty significant in the current is going to be very significant. When we deal with the current in there, like I said before, about 600% of the running current. So what that 600% means, we're going to have to increase. We're going to make these big. We're going to make these huge to handle inrush. And that's the startup current. Okay, and there is a procedure for that, and we'll watch that in some future videos coming up. But the overcurrent device is going to be made really big. And if we were to keep it like this, we're going to have to make sure that all our conductors are going to be sized based off of that ampacity that those things can protect. It's not feasible, it's not practical, because we know that it's only going to be an instant that those motors are going to be on and with that inrush condition. So now we're going to size these guys to be really big, and they're only going to protect, in this case, short circuit conditions. I don't know why I put an S in there for circuit. I guess I'm spelling it interestingly. Short circuit So they're going to have a really massive amount of current there, which they're going to trip. And they're also going to protect against like big surges. Everything else is now going to be protected here with our overload. This is now protecting the motor and conductors. Now, the overloads will allow us to have a small amount of time that they will be into allowing for that surge of energy, but we have to have them separated because our circuit breakers are too sensitive. They're going to trip as soon as they see anything beyond their rated value. We can use time delay, but it's still going to be beyond that. And we're not protecting our circuit properly. So we separate it between overcurrent and overload. The other thing that we want to take a look at is the terminal numbers, because our motor starter essentially is a contactor that has overloads. When we come into our circuits here, we come in with our line conductors into the L terminals. And we come out of those terminals with our T terminals. So again, I'm going to go from my red and we're going to go down into our motor, black and blue. So we're coming in with the lines and we're out with the T's. Now this is significant because essentially what we're doing is now we're protecting those conductors. We're no longer line conductors that would be unprotected. They've gone through the contactor, the motor controller, and they are now protected to some degree. So these guys right in here are our overloads. I'm just going to highlight these guys. That is our overloads. Now what they are is they're sensors that they are in line with our motor itself, and they're actually measuring the current that's going to that motor, and they're going to adjust accordingly. Now there's different types of overload sensors and overload reaction. We can either use magnetic or we can use thermal. Either way, they work. Some work better than others. Some work a little quicker than others. So it all depends on what you want to pay for, but they're two separate things that we are looking at. Our overloads versus our overall overcurrents. The other thing that I want to identify here is that when we are looking at our motors, I just want to set a general standard. When we look at the motor currents, we want to have a look at what they call the full load amps. That is the running current that is based off of the motor shaft. Our horsepower is always based off the output power. The output power of that motor. It doesn't factor in the input. We would have to consider that after. But the output power, this is either going to be provided as nameplate information. So I'm just going to say nameplate info first. Because nameplate, who knows those motors better than the people that made them and engineered them? Now, when we look at the code book version here, if we don't have a nameplate information, we're going to go to tables 44 or tables 45. In those tables, you're going to be very careful because we want to make sure that we're reading. Table 44 is for 3-phase. Table 45 is for single phase. If you were to do a comparison based on the same voltage, just choose like 230 volts. 230 volts for a 7.5 horsepower motor for 3-phase is going to draw 22 amps. If we were to go to table 45, it's going to draw 40 amps. Under single phase, we're going to use a lot more current to do the same amount of work. There's a reason why three-phase power is used so much more, because it's much more efficient. So one of the things that we want to look at when we're dealing with all of this is efficiency. Three-phase versus single phase, no question. Three-phase is more efficient. We're going to get the same output power with less cost, less material cost in our conductors, less overall cost for everything. I hope this helped.